Okay, frequency response, part 2, and we're dealing this time in this section with Bode plots, a very standard, well accepted, as well as a very good way to plot frequency response as a function, transfer function response with regard to frequency. So simply put, Bode plots are semilog plots. Semilog, which means one axis is logarithmic. That'll be the frequency axis. And the other axis is linear. That'll be the magnitude or phase, whichever one. So it's a way of compressing. Frequency can grow rapidly, and a lot of the effects only take place when you double or quadruple or multiply by 10 the various effects. So you really need to have a compressed, in a visual sense, a compressed frequency picture. So take the basic transfer function, has a magnitude and a phase. That's all we're saying here. Pretty easy. And I want to take a moment and remind you what it represents. So a phase angle, remember, can be shown. A phase angle can be shown here with Euler's identity, right, as an exponential, right? So that's going to be important. And the real part is cosine, the imaginary part is sine, as we've always had. But this is the important thing right here. There's an exponential representation of a phase angle. And Bode's going to take advantage of that in this way. If we take, actually, I guess we can then express it here. I can say for a moment, we're going to express our simple thing. We're going to express that as the magnitude and the exponential. And then simply take the log of both sides. That's all that's happening here. And the log of a product is the log of the sum of the logs of the individual items. And this is, of course, true no matter what the base of the logarithm. Here the base is going to be e, and you can see how nicely this is going to head. So the log of h will remain, but the natural log of e to the j phi will just be j phi itself, right? So this is all, it's a way of just separating the terms and straightening them out real nice. So we'll be able to plot these separately as a function of frequency. And so a way of a common practice, I know you've all heard this over anything having to do with audio equipment or noises in places. The the magnitude can be expressed in dB. We talked about that in the end of the previous lecture. And as a general magnitude, since we're not talking about power, we're talking about 20 times the log now to the base 10. Notice we changed this. That was consistent with decibels. 20 log to the base 10 of h. And this makes h not a power function, right, according to our previous discussion, but it makes it just a magnitude function. All right, here are a chart. I just grabbed this out of the text. Worth noting because many of these values are really recurring and important to us. So for instance, here's one of the first ones, this and this. When the magnitude diminishes by the square root of 2, that turns out to be minus 3 dB. When it increases by the square root of 2, that's plus 3 dB. All right. Another important one is when it doubles. We like this. Magnitudes double, that is 6 dB. And of course, when it goes to half, that's minus 6 dB. So those are some real common ones. The rest of these are multiples of 10. and then of course the one of 20. This is less common in my experience, but the square root of 2 raising or reducing, and the factor of 2 multiplying or dividing by. So plus and minus 6 dB, plus and minus 3 dB, really commonly occurring values that we're going to want to pay attention to. All right. Now, if we look at this, which is rather horrendous, every time I see this or something like it, it always, I see the most number of Greek and strange symbols in here that that I quickly want to get rid of. But we have it, the standard form, and really what it means, what's trying to be conveyed here by the standard form is this: there's a constant term, okay? There's a single frequency term, so a linear frequency term, or just the multiple of omega, to the power of plus or minus 1, right? So that's easy. Then there's a simple root, right? A single root. Term, right? Where once you solve for it, you can find the root. And there could be many of those. And then there's the quadratic. Okay, and the dot 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 means this can go on, this can go on this way to something having a blah 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 to the third, and another one to the fourth. You can keep doing that. And for reasons you'll want to see, and the same thing can be happening in the denominator, right? Except the constant usually isn't there. And we'll be wanting this because we want to know, whoops, where am I? We want to know where these roots are. So this will be a quadratic with 2 roots. And it's always going to be the roots that are important. Same thing goes on down here. We're going to want to know where these 2 roots are. And here's another one. A root. One root to that term, right? And in fact, if we took quadratics, we could find the roots, and then we could write that as the product of 2 single root terms. And that would be nice. And ultimately, we're going to want to do that, all the way through the numerator and all the way through the denominator. You remember earlier we talked about functions being of the form, where am I here? Functions being of the form, the numerator of omega over the denominator of omega. And we like this. We're going to try to expose all the roots in the numerator and all the roots in the denominator. And the reason we want to do that will become obvious here. Remember, the roots in the numerator are what we call the zeros. And in the denominator, the roots are the poles. Just terms. These drive to infinity, right? And these drive to 0. Okay. Now that's just the standard form is just a way of expressing mathematically what we're aiming for. All right, there are 4 forms that will then occur, or can occur. The first is the constant gain. That's the easiest, right? Where y equals 500x, or x equals 500y. That's a constant gain. The second type will be a simple pole, 1 pole or 0, but at the origin. Okay? So in other words, omega is 0. That's the item that satisfies it. Would be like this term. Okay? The third case will be a simple pole or zero. In other words, a single pole or zero. So you have this business. It's referring to this right here. You have that business in the numerator or the denominator, like right there. Okay? So we have a single, you can see here the answer to this would be when omega is z1, or here when omega is p1. And then we have the quadratic pole or zero, right? The pole or the zero, but it's the quadratic. So these are the two cases, the two roots. Okay, and usually the roots are tightly coupled, so they cause a particular frequency effect, whether they're in the numerator or the denominator. So it's broken down into these four basic cases that we're going to discuss. All right, the first one, the constant gain term, I think is pretty straightforward. It can be expressed this way. With constant gain, of course, there's no change in frequency. Right, here it goes. There's no change in frequency, in phase with the frequency. Now here you see the semi-log business going on. See, the space here, the linear space is some x, and it recurs here if you're not familiar with log paper or log or semi-log. So that distance linearly is the same, but the magnitude changes by a factor of 10. Same thing over here. And if we take 20 log, if we have constant magnitude, 20 log of the constant is what? That's the decibels that we're plotting for a constant k, right? So if k is very small, and we know from that table that we had, if k is very small, you can 20 times that, you can end up with your plus and minus 3 dB and those kinds of points. But this is a constant, unchanged, not changing with frequency. All right, the second one is the pole or zero at the origin. When there's a pole or a zero at the origin, let's just take the zero, then the transfer function has the form j omega, right? And two things we can notice about this. First, the phase is always 90 degrees, right? Zero at the origin means, the frequency that satisfies it is very, very small, right? So remember now, we'll be plotting for h. We'll be plotting the what? H is 20 log 10 of omega, right? That's what we're going to be plotting here. Whoops. If I can find my pen, there we go. So h is going to be, in dB, is going to be 20 log 10 of omega, right? And what are we going to notice here? We could go back to that chart, but we only need to pick a few points. When omega equals 1, right, the log of 10 equals 0, and so the dB is 0. Right? When omega is equal to some other larger number, right, we're going to want that. We'll want to know, we could ask ourselves here, what will make omega equal to 20? Well, when the log of omega is 1, so when omega is 10, the log of 10 is 1, so the dB are going to equal 20. All right? And similarly, see, now this is the business about the log scale instead. If we want to go the other way, we could say if omega is 1/10, right, then the log of 1/10 is what? Minus 1. So the decibels will be, whoops, minus 20. All right. Now notice what's happened. We've got 20 log of omega. If you look at these by compressing or by plotting on a logarithmic scale, it's not really compressing. We've actually kind of linearized. It's not a linear function, but we've linearized how the plot looks. So we now have 3 points here, right? And if we say we're plotting now in dB, so we've picked 3 points at 20, 0, and minus 20. And we've got, let's just pick a couple of points spread evenly here, where we've got 0.1, 1, and 10 on the logarithmic scale, right? So this guy is a point down here. We calculated that point, and we calculated that point. So here's our line. Notice this is a straight line with a slope of 20 dB per decade. Okay? Now, when we know that's going to happen, we're going to want to find out how do the poles and zeros change this slope, right? If it was constant, there was no slope. Now we have a single pole, or a single zero in this case, right? And the poles can be done in exactly the same way. Here are the pretty versions of what I just did, but you can see it. Now, if they were poles, they're very similar things, except what? Everything is inverted. They're down below. So if I wanted to plot the pole here, whoops, I would have the same idea, except here goes the slope like this, minus 20 dB, right? Because we're actually plotting 1 over JW. So it's minus 20 dB, and the phase would be equal to minus 90 degrees. Okay, for a pole. This is for a pole at 0, or at the origin, I should say. Okay, it's not really 0. It's our origin of 1. And on semi-log paper, the origin is 1. Okay. So now the simple pole, or 0, we'll take the 0, and the changes to the pole will be pretty obvious. Okay, so initially, we have this for the pole. Remember the standard form, and we extract the single pole. In other words, we're looking at a term that has something like 1 plus j omega, and in this case, it's already been extracted as a 0, right? Some constant term here, right? That's how we're used to seeing it, right? Almost like a 1 plus j2 omega, something like that. Okay, but now it's being put in a nice special form so that it looks like this. It looks like omega over the 0, right? So what I have here might be written as omega over 1/2, right? To get it in this form right here. So we're extracting that. We're trying to set it up so that we can easily identify exactly where in frequency terms the 0 is. All right, now let's take a couple of cases. As omega approaches 0, in other words, as it gets low, you approach DC. As it gets really low, you have 20 log of 1, log to the base 10 of 1, right? So this form, omega over z 1. If omega itself just goes to 0, forget what the value of z1 is. If omega goes to 0, you're just left with 20 log of the magnitude of 1, which is 1. All right, and that's 0, so that fixes 1 point. All right, we can take the same thing. This is the same expression. But now we're going to look and say, what if omega gets very large? Right? When omega gets very large, we get 20 log of omega over z1. Now z1 plays a role here. See? Here, z1 has no role, right? Because the frequency is all very small. Now when it's large, z1 is involved. So you can see we're going to be looking for where are the points, where are the frequencies that matter. And it isn't whether it's high or low in terms of our ability to hear or a dog's ability to hear. High or low is relative to the terms like this, to the zeros or to the poles. All right? All right. Let's do the same thing with the phase. Now the phase, remember in our first term, we took it out and we were able to say that the phases can be expressed as an exponential. And oh, by the way, it's that exponential is always of this form. What have we got here? We've got the sine theta, cosine theta plus j sine theta. And whenever we find the angle of that, we're right back to this, right? So we're right back to finding our inverse tangent of the ratio omega over z0. So here's a couple of quick cases. When omega is 0 or very, very low compared to z0, the frequency is 0, right? The tangent of a very small angle. So you can just kind of look at that triangle, right? When this distance here is small, when this is low, this angle is 0. As this distance grows and this thing, right, gets bigger and bigger, the angle grows. And so we have that. When it's equal, you have the tangent of 1, so that's an important number, 45 degrees, right? When this distance is z1, and this distance is z1, right? And then as it gets bigger, it heads toward 90 degrees, right? And that's to be expected. You remember the plot of the tangent is that thing that stretches to infinity in both directions, and then and goes through 0 on the way. All right. So if we try to plot this, then the simple pole, rather than draw it, I'm going to use their pictures from the text. Couple of things to point out here. Notice they show the exact curve. There it is, nice and smooth, right, for the magnitude. This is this guy here. This is a smooth function. But in Bode plots, we're going to notice we know where this key point is, right? The 0. The 0 of the standard form. And we know that below that, and you see it here in the exact picture, below that it stays at, we're gonna approximate it as a constant. And then we know that after that point, since there's only a simple 0, a single 0, that it's going to move at some frequency or some ratio, and this is going to be what? At positive 20 dB per decade. And we also know that this point of the 0 in real terms is the 3 dB point. Okay, and we looked at the frequency of the phase response of the angle, and once again the exact shape down here. This looks more like our tangent shape. You know that if you turn this up, where the tangent is 0 and then it cranks through 45 and then it goes smooth up there. The exact shape is very smooth, right? This is the smooth tangent curve. You know, just like you look in a trig book or trig tables or whatnot, you'll see that. We're going to approximate it as a straight line, right? And we're just saying here what goes on. If I'm at the 0 point, I looked over here and it's 45 degrees, right? So I know that point. I also know that when it's really low, and so here we're calling it 1/10. This is going to be our approximately 0, right? That it's essentially at its low 0 angle. There isn't any point in carrying it on and on and on because you're dealing with fractions of a degree. All the interesting activity happens in this decade, right? Right here, this decade of frequency. Okay? And then the other half occurs in this decade where it finishes out to 90 degrees. Right? Another decade. And so you can see a couple of things are implied here. 10 times the 0 is acts like infinity. Right? That's this term here. And 0.1 times 0 acts like 0. So we don't have to take it out to infinity or crank it way down. And this is going to be important to consider. All of the meaningful action happens within, right, in this time frame. For a simple pole, the same is true for a simple 0. Remember, these slopes will invert. Right, the slopes will invert. But plus and minus a decade is the action. All right, and when we have several zeros or several poles, they might overlap and interact with each other, but the important thing is each one has its influence at plus and minus 1 decade, right? Now, if I took poles, I would be at zeros. You know, this phase would look like, what, the same thing, except it's going to head down, right, at 0 and minus 90, right? And this will be a minus 45 degree per decade slope. And this will go from, you know, this horizontal, and then it will break down at minus 20 dB per decade for the pole, all right, the pole. Okay, so we have one more basic case to consider now. All right, so in the final case, the quadratic pole or 0, let's bring up, let's do it as a pole. And you can see that's kind of going to be evident here from the minus that we're considering a pole. But here's a quadratic, right? And it's got a bunch of terms, but ultimately it's our squared term. And here's our omega n, which is going to be the basic, you know, where something about the roots of this equation are related. And let's take a look at this. As omega approaches 0, in other words, that's a tenth of whatever the pole values are. As omega approaches 0, so we're looking at the top term here, that and that are going to go to 0, and we're going to end up with our typical minus 20 log to the base 10 of 1, but that log is 0, so irrespective of being plus or minus 20, we're going to end up with 0 as the number of dB magnitude. Okay? In the case of omega getting large, right? So this is large with respect to our pole locations. The magnitude expressed in dB, because it's now a quadratic, is 2 times 20, right? So we're looking for quadratic poles are generally going to be what? Plus and minus something. Remember, the roots of a quadratic are minus b, right? The roots of a quadratic minus b plus or minus square root of b squared minus 4ac all over 2a. The point is, you have some constant value and you're plus and minus around that. Okay? So as that happens, then, what this is implying is these two roots in a quadratic term, one that doesn't factor nicely but factors to a quadratic, you've got a pair of roots that are operating together. They somehow are influencing each other. And as you'll see, this works out to be just this way. That we say there's minus 40, but there is still this single key frequency around which things rotate. They bend, or that sort of thing. All right? So here's what that looks like. Notice there's this extra term that got brought along here. This, where is it here? This guy right here. It got brought along, and as that value changes, right, as it changes, right here, we're showing that, the sharpness of the peak around omega n. So here we are with this one determined frequency. Here we are where we're safely back, so 0. Here we are at our infinity, right? This is our 0. And there's our center point. So we're going to, in Bode terms, keep our same shape nice and flat through here. A corner, and we're going to call those corner frequencies, and a fall. This is exactly the same shape we had when we had a single pole. All that's different is we now have a different slope, 40 dB per decade instead of 20. And in real life, the angle of the curvature, if this squiggly term, I've forgotten what the letter character is, but if gamma or something like that, if that term is high, greater than the square root of 2 or higher, the smooth curve gets slower and slower and slower. But in terms of design purposes, what we're concerned about is, where is this corner? And this is called the corner frequency. Not just for the quadratic terms, but also for the single poles and single zeros. The corners are where the action is, and that is why the standard form breaks them out and tries to identify them. Okay? So terms that are triples or quadruples will have really strange real-life action here. You know, this shape will be really strange looking, wicked looking, but you'll still end up with a corner, right? And what will happen is this thing bending at minus 20, minus 40, minus 60, minus 80, right? That's a function of the complexity of that power term. And in this case, we're just taking it to the second power. Okay, let's look at the phase angle. The phase angle now has, here's our what would have been the real and the imaginary parts. All right, so the same thing going on here. And the terms now are this. At our 0, so in other words, remember this is 0.1 omega n, and this is 10 omega n. We just end up with 0, but now this is doubled. Used to be minus 45, now it's minus 90. This used to be minus 90 as the target, now it's minus 180. Okay? So you get the idea. The angle of bend changes. Here you can see, the real angle of curvature. This is a function of, I think this is a gamma. It's a function of gamma, the angle of that curvature. We're going to approximate all of those independent of what gamma is. We're going to approximate them all as a straight line. And all we care about is where's the corners and where's the pivot point. Right? So there's the corner. Those are the things we care about. And then what's the slope? And we know those because we know the power of the term involved. If it was a quadratic, the slope is doubled. Here the slope is also doubled, both in phase and in the magnitude plots. So that's the basics. And we're going to learn how to sketch these things pretty much, by looking at them, maybe having to find those. We might have to calculate with parts where those corner frequencies are. But once we got them, we can plot the responses as Bode plots. So let's do that. Okay, so now we're going to be doing a couple of practice problems. And these are very pictorial, which is really one of the big assets of Bode plots. And what we have to do in any given transfer function is just isolate and get it in standard form and recognize where are the poles and zeros. So let's do that here. See if I can get my pen going. And I'm just going to start this to go along with the examples in the book. So I'm going to factor this item, and I don't need to recopy it. I'm going to factor out the 2 in the numerator, right? So it's going to be 5 times 2 times 1 plus jw over 2, right? And there's that standard form of the simple polar 0 showing up, 1 plus. That's the standard form, 1 plus. Because when the omega hits this value, you have 1 plus j1. And that's what you want, because then you have the square root of 2 involved, and you have the angle of 45 degrees. That's what we're aiming for in all of this. All right, so then I've got JW, so that's a pole at the origin. And then I'll factor out 10 from this one. And I end up with 1 plus j omega over 10. Okay, so we've isolated those two. You can take the 5 times 2 is 10 and divide out that 10. That's okay. That's a constant term, right? Let me take I'm not sure we need to even go greater than this in terms of sum equals. We see right away we've got 3 terms going on here. 2 poles, one at 0 and one at 10 over here, and another 0 at 2, right? So let me just make this statement so you see what's going to happen if you haven't by this point. So the h of omega, we're basically in the standard form trying to get it into a bunch of little transfer functions. So h1 in the numerator times h2 times ... over hx times hy times ... in the denominator. All right? So we make this as the numerator as a function of a bunch of little transfer functions each of which are, hopefully, each is one of the 4 cases that we talked about, right? The constant, the origin, the simple polar zero, and the quadratic. Okay, that's what we're trying to do, is get those points. And then what happens to this? When we take logarithms, logs of products are sums. Okay? So you can see it happening. We're going to make, so we're going to make, the plan here is to make individual plots of the numerator h's and the denominator h's, right? And then we'll add them graphically. Right. Because we know a lot of the key characteristics, what the break frequencies are, what the corners are. We just isolated all of those up here, what the corners are, and we know then where the rates at which they fall or rise, right? Minus 20 degrees, 20 dB per decade, minus 40 dB per decade, that sort of thing. And the angles drop at, they're fixed rates. Okay? So let's just bring up the first of these rather than draw it all. The answers are there in the text, which is nice. I just want to help interpret them because you'll see how easy this process becomes. So here, let's look at the numerator terms. Right? In the numerator, we have this guy, right? This is the controlling numerator term, the H1 in the numerator, right? And it has a break frequency of 2, and it's 20 log, well, the magnitude was 1, so it's 20 log. So here we are, just doddering along. Here is that curve, right? The dotted line that they've nicely done. That takes care of this term. Now let's go to the denominator. We've got a pole at the origin. There's the origin. Okay, and here's the pole, so it falls at the rate of 20 log 10 of 1 over JW. But we know that's 20 dB per decade. And so here comes that term, right? So this is H, the first term of the denominator. And then here is going to be the second term, H2 of the denominator, right? So back up here, I'm going to call this one arbitrarily H2 and this one H1, right? And this thing here is the numerator one. If there'd been more, we'd put them. Okay, so now we got all these dashed lines. Now look at the red line. It is the simple sum of these. Notice this, the original controlling one is this H1 in the numerator right here. This starts at all the low frequencies. There's nothing in the numerator that's going to pull it up. So the denominator controls, and it's falling. Okay? It's falling. All right. At 2 is the first meaningful breakpoint then. That's in the numerator. It wants to pull it back up. So when we add these two, the falling one and the rising one, right here at this corner, there's the corner reflected, but now we're at negative dB. So we're moving along here. Just the sum of those two. At 10, 1 decade out, it now encounters another fall. So Here, it's the sum of these three. From here on out, you're adding this and this and this. You were actually adding all of them before. It's just that H2 never had a non-zero value until it got out here, right? And H1 in the denominator always had this going on. It just basically was always trying to pull everything down. H1 in the numerator was 0 until it hit its breakpoint, and then it started to go up, all right? And you might remember from the individual pictures, these things actually have shapes like this. So if you really wanted to be fancy and clear, you would add up those things. But Bode makes this simple. It identifies, look, the important information is where are the corners, what are the magnitudes, and what are the rates of change. Okay? The same thing can go on with the angle, right? We can look at how each of these terms affects the angle. So here's phi of w, right? And it is going to be, we have the fixed minus 90 from the pole in the denominator, right? And then we've got the next thing that occurs is the 0, right? So we've got the tan of minus 1 of omega over 2. And then there's another pole that happens, tan, inverse tan of omega over 10. All right, and that's what's being displayed here. Again, we're just adding the pieces together. Here's our original guy, starts at very low frequencies and controls the low frequencies. Once we hit the first breakpoint, right, once we hit the first breakpoint, we start to experience the omega over 2 term. So here's our numerator term right here going on, right? Now you notice these pop in presumably or apparently a decade earlier. Here was omega over 10, but oh, it's coming in at 1. Well, that's, remember, because the tangent function stretches out to infinity and minus infinity if you plot the tangent function. And so if you try to plot that over frequency, you're really at 45 degrees here, right? The breakpoints turn out to be 45 degrees, right? If I have, here's this first one. If I follow it alone, the breakpoint of 2 is right here, right? So you're at 45 degrees. That's what's going on, right? That's what you got to remember. It's not that, like in frequency, the breakpoint is where it actually starts to move in its positive or negative direction. With the angle, the breakpoint is where it's 45 degrees. Okay, and up here you can see this one. This is where the tangent has effect at plus and minus a factor of 10 around the breakpoint. After that, the tangent is flat out at 90 degrees. And before that, it was flat out at 0. Okay, let's try another. 14.4. So here we've got a similar thing going on. We can probably move through this quicker now because we're getting, you can see once you do a few of these, you begin to see what are all the key points, right? So we can break this up. Actually, I'm going to just mark this up. Here you've got, quite obviously, a 0 at the origin, right? And here you've got, oh, look at this, you've got the constant k. That was one of our 4 cases. Here we need to change this into what? 1 plus j omega over 4 times 4. And this will become 10 times 1 plus j omega over 10. Okay? So we could, we now can identify that we've got, oh wait, this was a square. Hang on. This was a square, so we can pull out 10. So we need to pull out 100. Oh, so what we're looking at now is the standard form of the quad term. That's what we like. Okay, so there is that. And so now we've got, this one actually represents all four of the components that we talked about before. So here's the quadratic, that is, at omega equals 10. And here is the simple at omega equals 4. And then we would have the product here of 400, right? We could pull all that together, and we'd end up with something like what, 1 over 8, right, times the JW times the 1 plus J omega over 4 and 1 plus J omega over 10, the quantity squared. So now if we just start looking at these, we need to know what to expect. So here's the constant term. So I'm not going to worry about that. That's just going to be an offset, right? A basic offset. Here's the 0 at the origin. So you're going to see something rise at 20 dB per decade. Here you're going to see a fall. I can put it down here. This is going to be the interesting one, right? This is going to be a fall at 40 dB per decade. All right, and this is going to be a fall, of course, at 20 dB per decade. So we should be able to plot those without a whole lot of mystery. Before we get too far along, let's also do the phase angle, right? So here the phase angle is going to be, we've got a 0 at the origin, so that's in the numerator, so we're going to have 90 degrees. All right, that's where things are going to start. As frequency rises, that's going to get challenged. We've got the first pole to occur as frequency rises is going to pull the angle down, right, according to the inverse tan of omega over 4, right? And this is going to vary. This point, recall, is going to be 45 degrees. So it's going to go from 0 to that to 90. Whoops, to 90 degrees. Then we've got a double pole at the frequency of 10. So we'll have 2 times the tangent of -1 omega over 10, right? So this is now, because it's doubled, this is actually going to go from 0 to 90 at the breakpoint to 180. Okay, because we're doubling that angle. So you'll see that in the various plots. So let's take a look. Here's the magnitude being plotted, and here's our first guy. Where's the pen? Yeah, here's our first guy right here. Here's that numerator term. Okay, the frequency component is going to be that. Okay, here, by the way, just so you know it isn't lost, this one right here is our 1/8. Okay, and because it's a fraction, you're going to have minus 20 dB log of 8. Okay, but that's what's going on with that term. So we didn't lose our constant. There's the K. And then we've got, so there's the numerator terms right here. This is numerator 2. This is numerator 1 if we wanted to label them. Then we've got 2 terms in the denominator. The first one that hits, right, is this. Here's our denominator at 4. And what's happening in the magnitude, it just breaks at 4 at minus 20 dB per decade. Okay, it's just falling. They don't label that here. It's just a number. If you do the math here, the negative sign will be added because this is a fractional component, right? Fractional component. This, just so you're interested, this could have been written as 20 log of 1/8, right? Which is what's happening here. These are 20 log of 1 over the magnitude. This is 20 log of 1 over the magnitude. Okay, and then we've got at 10 comes in, so this is denominator 1, and this is denominator 2 in the obvious way. Okay, and let's go on then with our phase. Here was the phase. It starts at 90. Then it gets influenced at 4 and gets influenced at twice the rate at 10. So here's our original term up here. It starts at low frequency at 90. At 4, here this kicks in. And then at 10, this kicks in at twice the declining rate, right? When it gets way out here at 10 times 4, so where are we? Here was, let's see, where are we? At 10 right here is the midpoint, the 45 degrees of that falling curve. You got to get these separated. The omega equals 10 is going from 0 to 180. So at 10, it's going to be closer to 90. I'm not sure this is well drawn here. That's this guy. I'm sorry. Whoa, that's this guy. Right. I got the lines crossed here, and I didn't see it. So that's this one. So this is denominator 2. Here's denominator 1 term. All right, and then here's the numerator. The numerator, we called that 2. The numerator 2 term. And the constant doesn't provide anything in the angle department. Okay, so again, here's the one that goes for number 4. It stretches down here away. So notice at 4, this guy is at 45 degrees. At 10, which is the break frequency, this guy is at 90 degrees. So when you have a bunch of them in the denominator or in the numerator, it is best, I've found, from doing it wrong a lot, draw each of the plots separately and then do the addition collectively when you've all got. And they've done a good job in the text of doing that with the dotted lines. Okay, so I think we'll quit here with examples. The examples in the text are excellent. And in the final one, which is going to proceed from now on, we'll be making a substitution for S equals JW. And what that does is it just makes real clear simple factors where you've got, 1 plus AS plus BS squared, this sort of thing, right? You get really simple quadratics, and just makes it, you get rid of all the J's and the W's, because we already have analyzed it. We know from the 4 cases what the J is going to do with both angle and frequency. Okay, so we'll pick up now next time with resonance, another part of frequency response. All right.